Today's objective is to explain the relationship between cryptographic keys and passwords. So today we're going to dig in a little deeper to how this idea of using different keys actually works. It's a big deal that asymmetric encryption allows for two parties to send secret messages to each other over public channels without having to agree on a secret encryption key ahead of time. Now let's look at the mathematical principles that allow private and public keys to work. Your think right share here is, what did I just say asymmetric encryption is? So at the end of the lesson, you're going to be given a mathematical formula, and you're looking for a key to make that formula work. Not necessarily the right answer, but the key. So how can we send messages back and forth without ever meeting beforehand to discuss the way we're going to encrypt something? Well, through Modulo. Think of Modulo as a clock. Modulo is an actual math operation. That is to say, it's the remainder after division. So it looks like a percent sign, and it almost looks like a division sign if you squint real hard, but it's its own sign. It's its own mathematical operation. The clock is a useful visual to think about, but the size of the clock is arbitrary. The same principle of wrapping around the clock would apply no matter how many ticks were on the clock. So what I mean by that is, here you have 12 spokes or 12 ticks, and depending on what you're using modulo on, this number can change. So if I had like 24 modulo 13, I would need 13 ticks on the clock. So I'm talking about this clock because what this clock would do is give us a one-way function. A one-way function is a math operation that is impossible to reverse or solve even if you know some of the inputs that went into it. But it's not random. Given the same inputs, it will produce the same result every time. There's just no way to reverse the process. So your think right share here is, what is a one-way function and how is modulo related to this concept? Let's say you're struggling on that second question. I think I'll answer that right here. Imagine that you're a person who loses complete track of time when you close your eyes. Anytime you close your eyes, you just have no idea how much time has passed. It could be an hour, a day, a week, a year, you just don't know. So now imagine a clock that reads 4 o'clock. When you close your eyes, I'm going to add some time to that clock. So let's say you open your eyes and you see it's 3 o'clock now. Your think right share here is how much time has passed. So how much time has passed? What are the possibilities? You may be shocked to hear this, but I was imagining that I was adding 13 years, 47 days, and 11 hours to the clock. You see right there where it says 11 hours? That essentially means that as long as I am adding some sort of time and 11 hours is the number of hours I'm adding, the clock will forever read 3. No matter how many years or days has passed, as long as it's taking in 11 hours somehow. So the way this could look is, it's 4 o'clock now. All right, imagine 11 hours has passed, now it's 3. So it could have just been 11 hours. It could be 500 years and 11 hours, and for 500 years the clock has been spinning, and when you open your eyes, it's back to the 3 because it was 500 years plus 11 hours. So some of those numbers could be not only 11, but 23, 35, 47, etc. until infinity. Key points to take away from that thought experiment we just did. Number 1 is that modulo is a math operation. The clock is a visual for you to use to think about that. And the same principle of wrapping around the clock would apply no matter how many ticks were on the clock. Okay, so your takeaway is that the clock is a one-way function. There is no way to know the original input just from looking at the face of the clock. No matter what number you put into it, only numbers 1 through 12 can show afterwards. And even if the number is 2 million hours, if you want to wind the clock around, it will still come out as the number 1 through 12. We cannot know what the original number was that went into the clock. Now the clock itself is just a metaphor for modulo. Real cryptography uses this clock technique to obscure information, but with clocks that can have a wide range of possible values on their faces, the operation is called modulo. A modulo is a math operation. Okay, so I've spent quite a bit of time here just trying to explain that this is a mathematical concept, and because of this math magic, we are able to encrypt things. So your think right share here is explain to me how a clock is like modulo. To wrap things up, I'll give you a mathematical formula that actually looks more like what they're using in cryptography. So when you combine multiplication with modulo, that's how we'll get the computer to work on something that's called computationally hard problems. So guessing the blank value is pretty hard in this. A times something mod m equals r. So it's hard to do this math even when you know what a, m, and r is. So for example, if I asked you to guess right here just the blank, what could it be? 47 times something mod 51 equals 1. So if you're following along with me here and you said, I don't know, that's correct. This could be many different types of numbers. Okay, so let's go ahead and take a step back and give you some math problems yourself to work on. So go to this link here. Once there, you'll see a screen sort of like this. So right here, mod and then a number. Whatever you put here is the number of spokes that your wheel will have. And you can do a variety of numbers and really change up what you're looking at. For the math problems I'm about to give you is you'll have a number here and then you'll do a mod to it, modulo to it, to figure out what the answer is. And you can speed this up. There should be a setting for speed. There you go. So let's turn it to the maximum speed here, 9. So when I take the number 500 modulus 24, I get 20. So let's play around with that tool a little bit. Here's your think right shares. Using a clock size of 50, write a list of 5 numbers that produce a result of 0. With a clock size of 50, how many total numbers are there that produce a result of 0? If the list is short, write it out. If the list is long, describe a pattern of what the numbers are. And the third thing you need to do is using a clock size of 13, can you find a number to input that produces a result of 13? If so, what is it? If not, why not? So go ahead and pause here and work on that for a bit. When you're done, let's check your answers against mine. This is actually easy. Anything you can divide 50 by without a remainder will work. So 50 divided by 5, 50 divided by 10, etc. And for the third one there, I just simply said, no, I cannot. All right, so let's try to mix it up here. Instead of changing the spoke, let's start changing the number that is being modulused by. So 1 modulus 13 is what? 10 modulus 13 is what? And you just put your answers here on canvas. When you're done, go ahead and check using this chart. No cheating now. And as you've experimented today, you've probably noticed that small changes to the input will result in huge changes to the outputs. Using a clock size of 57, let's multiply 2 numbers. We'll call them A and B to use as an input. Then make small changes to each one, A and B, while holding the other constant. We'll always use the formula A times B mod M. We'll start with A equals 20 and B equals 50, and M is equal to 37. So using that, here's the result. You get a single 1. So I want you to keep this formula in the back of your mind as we move forward. It was a pretty heavy math day, but for the sake of learning cryptography and how things are kept secret on the internet, so go ahead and choose one of these IB profiles to say the lesson was a characteristic of. And then here you go with a DOL thinking back to this phrase that small changes to inputs will have large changes to outputs. I want you to answer, why would a longer password be a better private key? And if you want some video assistance here, you could go to wimp.com. The video is pretty good, but it's basically my last-ditch effort to try to find ways to explain to you how modulus is so useful in creating passwords or private keys.